What volume of water must be added in order to raise the pH by 1 unit? So we want to go from pH 3, and that correlates to a hydrogen ion concentration of 1 times 10 to the negative 3. And we want it to raise the pH by 1 unit, which is going to be a pH of 4. And so we're going, and that would correlate with a hydrogen ion concentration of 1 times 10 to the negative 4. So what we're doing is we are decreasing this by a power of 10. Yes? So we're making it 1/10 of what it once was. Yes? So this is a case where you could, you can just intuit this and be like, if it's 1/10 of what it was, I need it to be in 10 times the volume. And if that's the case, if it needs to be in 10 times the volume to make it 1/10 of the concentration, then if it started in 1 liter, then it needs to now be in 10 liters, which means we needed to add 9 liters of water. But if you're not intuiting that, if you're like, whoa, what happened? That went too fast for me. You can use for this one, M1V1 equals M2V2, also known as C1V1 equals C2V2. And you can say my initial concentration is, we want what volume of water must be added to. So we want V2. So V2 is equal to M1 V1 over M2. Yes? So my original molarity is 10 to the negative 3. And my original volume is 1 liter. And so my final molarity should be 10 to the negative 4, because that's going to give me a pH of 4, which is 1 greater V2. And so that gives me 10 liters. Yes, so I start at 1 liter. My final volume has to be 10 liters, which means I needed to add 9 liters of water. Is that okay? Cool. But like I said, you don't actually have to do all of this. If you can say to yourself, this is 1/10 the concentration, so it must be in 10 times the volume. So like if you wanted to half a concentration, it would be in twice the volume, that kind of thing. You can just do it, without writing everything down for a multiple choice. Anything else? 26, yeah. Okay, so we want to go, what do we need to do to go from pH 2, which is 10 to the negative 2 molar H plus, to create a new solution where our H plus is 10 to the negative 4 molar H plus. So we're going from a higher concentration to a lower concentration of H plus. And so either we had to have neutralized it or we had to have diluted it. So to go from a higher concentration of H to a lower concentration, you need to either dilute or neutralize. So if we wanted to dilute it, we would add water. So there's our answer right there. To neutralize it, we would have had to have added some OH, but there is no option for adding OH. All the rest of these, all of those, would mean the hydrogen ion concentration would get bigger, not smaller. So that's why we can't choose those ones. And the solution does not already have a concentration of 10 to the minus 4. It has a concentration of 10 to the minus 2. Yes? Anything else? Alrighty. Anything else? No? Okay. If that's the case, then we will carry on with solubility, and we were somewhere around page, yes. Yeah. Well, it's no different than the regular stuff, really. Other than number 31, which is not. Nope. Okay. Number 31, not on the test. And number 6 is a bad question, and number 8 is a bad question, so make sure you omit those. Okay, 6 and 8, gone. 31, not on the test. All right, we were on page 27. And while we are here, do you remember what we mean by the term molar solubility? How much dissolves? Yes. I should say substance, not compound. What is another way to say how much dissolves? Concentration. Now, there's a little bit more to it than that, in that it is how much of a substance can dissolve, which means that we are looking at the maximum concentration. Does that make sense? Okay. So it's not just any old concentration. It's not just like chuck some in and that's the molar solubility. This tells you how much can dissolve, what is the maximum we can actually dissolve. Okay. So that is our molar solubility. It is a concentration. So molar solubility is the concentration of substance, whatever it is, you know. Okay, it is a concentration. Maximum. Okay. And reminding ourselves of that, what is KSP? What does it stand for? What does the SP stand for? S stands for solubility. And P stands for product. And if we're working with KSP, what kind of equation do we use? What kind of reaction do we write? We write the equilibrium. Yeah. What kind of equilibrium? The solubility, equilibrium, equation, the C. And in the solubility equilibrium equation, obviously we would need to have a what kind of arrow? Equilibrium arrow. And where does the solid go in a solubility equilibrium equation? It goes on the left. So here's our solid. And on the right goes our ions. So if I was to say to you, let X be the solubility of AB, could you figure out how to put that X into the KSP expression? How would we write the KSP expression? KSP is equal to concentration of A times the concentration of B. Oops, that's supposed to be minus. And the concentration of AB is X. I've put it in brackets because this is a solid, okay, but it still means like if we had dissolved 1 mole per liter, then it would be 1 mole, we would still say 1 mole per liter sodium chloride, even if it's all dissolved, right? That's just how we do it. Okay, so that's X. What does that tell us about A and B? They're going to be increasing by X. And sometimes we don't bother with the whole Rice table for solubility because it's pretty straightforward, right? Like these always start at 0 and they always end up being X at the end, or 2X or whatever. So you can often just draw it like this. Yes, Dylan? Yeah. So anytime you have a 1-to-1 ion ratio, then KSP is equal to X squared. Yes? What if we had a 1-to-2 ion ratio? What would we get as our products? A 2 plus and 2 B minus. And we could say sometimes instead of X, we will use S for solubility, okay? Be the molar solubility. And remember, what is molar solubility? Concentration. And generally, if we say solubility and we don't mention that it's not molar, like we can generally assume it's molar solubility unless we're told otherwise. But so if we let S be the molar solubility, then our KSP, our solubility here would be S. What would the concentration of A be? S. And B would be 2S. And what would our KSP expression be? That's not the KSP expression. What is the KSP expression? Concentration of A, 2 plus, times concentration of B squared. Okay? And so we would then get S, and we would have 2S squared, which then would equal 4S cubed. Now, this is really nice when it comes to multiple choice questions. Yes, because you don't need to show any work. You can just be like, I can just solve that. But on a written response question, I want to see this. On a written response question, I want to see this. I want to see this. I want to see this. And I want to see this. Each of those things in written response sometimes 0.25, right? Just because otherwise the question gets like, you can have 6 points for a question that doesn't really deserve 6 points, but you need to show all of that to prove that you know where this came from. Yes? Okay. All right. So let's take a look then at what we are looking at today. Oh, and by the way, would it be any different if I had A to B? If I had a 2-to-1 rather than a 1-to-2? It would still be the same. Okay, so anytime you have a 1-to-1 ion ratio, KSP equals 4x cubed. Anytime you have a 2-to-1 or 1-to-2, then KSP is 4x cubed or s cubed as you prefer. All right, now knowing that, we're going to take a look at, on page 27, if you have a KSP value, the smaller the KSP, what does that tell you about the ion concentrations? If we have a small KSP, the ion concentrations are small, low, okay? And if the ion concentrations are low, is it very soluble or less soluble? Less soluble. So we can say that the smaller the KSP, why KSB? KSP means fewer ions, means lower solubility. And what does solubility mean? Lower maximum concentration. Yes? Okay. All right. So compounds that are extremely insoluble will have KSP values somewhere like 10 to the negative 30, 10 to the negative 50, or even smaller. Crazy. Okay. So you can tell, as long as we have the same ion ratio, when all salts all have the same ion ratio, you can just do a direct comparison of their KSP values, and that will tell you which one is more soluble than the other. So say, for example, we went to our data booklet, and I gave you AgCl, and I gave you FeS, and I gave you MgCO3. Which of those three is the most soluble? Where would you look? Yeah, because we go over here and we say, okay, I can't just go here because this does me no good. It just tells me whether things are soluble or not. This table doesn't tell me which low solubility salt is more soluble than the other ones. For those kind of comparisons, we have to go here. And this tells us that our silver chloride has a KSP of 1.8 times 10 to the minus 10. And these are all in alphabetical order. So if you're looking for FES, you're going to look under I for iron. Iron sulfide is 6.0 times 10 to the negative 19. And for MgCO3, magnesium carbonate, 6.8 times 10 to the minus 6. So who is the most soluble? Yeah, so this is the most soluble. This is the, nope, that's the medium solubility. This one is the least soluble. And you can do that anytime you have a 1-to-1 ratio, because for this, in this case, KSP is equal to x squared, where x is the solubility, so x then is equal to the square root of KSP. So for all of these compounds, we will be calculating solubility the same way. Would we be able to compare AgCl with Ag2CO3? Not directly, because for this guy, KSP is equal to x squared. For this guy, KSP is equal to 4x cubed. So then if we're finding x here, x is equal to the square root of KSP, whereas over here, solubility is equal to KSP divided by 4, and then we would have to take the cube root. That cube looks like it should be x cubed equals, so I'm going to move that over a little bit. And if you're not calculating it the same way, you can't just say, if KSP is bigger, it's going to be more soluble. You would actually have to solve for x and compare the solubilities. Does that make sense? Okay. At this point, we are in section 3.2. Section 3.2 is all qualitative stuff. Even though we've been doing some quantitative things, section 3.2 is all qualitative. So for this section, all you need to know is that for these guys, you cannot just compare their KSPs. For these guys, because they all have the same ion ratio, you can just compare their KSPs and say which one is more soluble. And that's all you need to know for now. Okay? All right, let's go back here. So, out of these 3 salts here, first of all, are we able to compare these 3 salts? Yes. Which one is the most soluble? Barium fluoride, that is the most soluble. Who is the least soluble? Lead hydroxide is the least soluble. Okay? And so if we were to rank them then from the most soluble to the least soluble, you would say BAF2 is more soluble than Ag2CO3 is more soluble, and you could write over here more soluble, less soluble. And you got your little spectrum there. Okay? Would we be able to compare Al2CO3, 3, Cr2, SO3, 3, and Mn3, PO4, 2? Would we be able to just compare their KSPs? Yes. we can just compare KSPs to find the relative solubilities. There's no math necessary. Please tell your partner, what do I mean by relative solubilities? What do I mean by relative solubilities? Solubilities relative to what, sorry? To what you're comparing. Yeah, you're basically just comparing the solubilities to each other. Okay, I just bring that up because sometimes people get thrown by that language, but can we compare silver chloride, calcium carbonate, lead sulfide? Yes, because the ion ratios are all the same. Can we just compare the KSPs for AgCl, calcium hydroxide, and manganese phosphate? No. We would need to do math to find their relative solubilities. Yes? Cool, cool. All right. And this just lays out for you exactly what you need to show to get full credit. You need to show the solubility equilibrium equation for any KSP type question. You need to show the KSP expression. Could you please, for this question, write the KSP expression? What is KSP equal to? Concentration of Ca2 plus times CO3 2 minus, and there we go. Okay, so you need to, oh, that did not highlight. That's worth 0.5 marks. That's worth 0.5 marks. Okay, so let us write the KSP for MgOH2. You would get a half a mark for this, and you would get a half a mark for that. And of course, the coefficient goes there. Nothing new here. I'm not quite sure why I did a second example, but there we are. Okay, and that's it for that. And we're moving on to page 30. Okay, before we start here, I would like you to tell your neighbor, to the best of your ability, what is a saturated solution? What does it mean for a solution to be saturated? Yes? Yeah, you have the maximum amount of dissolved solute. Do you remember any other context in which we were talking about the maximum amount of solute dissolved? Yes? Yeah, if you increase temperature, you can dissolve more. It wasn't what I'm looking for, but that's okay. That doesn't matter. If you have AB, solid, you can dissolve more if you increase temperature. What does that tell you? And it's not 100% of the time, it's most of the time. What does that tell you about the process of dissolving ionic compounds? Normally, is that process endo or exothermic? Endothermic. But we were just talking earlier today about a situation where we had the maximum amount of dissolved solute. When we were talking about the molar solubility, right? Because the molar solubility is the concentration maximum concentration of a solute, which means that molar solubility is the concentration of a, yes. Sorry, go ahead. Yeah. So what that means if molar solubility is the maximum concentration of a solute, and if a saturated solution contains the maximum amount of solute, then molar solubility is the concentration of a saturated solution. So if you were wanting to find the solubility of a compound, you would probably want to make a saturated solution. Okay? Now, what does it mean then to be unsaturated? If a solution is unsaturated. Yeah, we have less than the maximum amount dissolved. So here we're starting with the unsaturated case. Okay, so we've got our unsaturated solution. It contains less than the maximum of dissolved solute. And if we have an unsaturated solution and if undissolved solute is present, are we at equilibrium? No. Because in order to be at equilibrium, we need to have what kind of a solution? Saturated. Okay. If you have undissolved solute present, so if you have an unsaturated solution and undissolved solute present, we are not yet at equilibrium. And if we are not yet at equilibrium, Which rate is faster? Forward rate is faster, right? Because we're dissolving faster than we are recrystallizing, which means that the concentration of ions will go up until we reach saturation. Yes? So the rate of dissolving is greater than the rate of precipitation. And if we were to graph that, there's no room to draw a graph there. What am I trying to do? Where can I draw a graph? There. If here is the rate of dissolving, and here is the rate of recrystallization, what's going to happen to the rate of recrystallization as time goes on? It's going to curve upwards because we're making more ions, and if we have more ions, more can recrystallize. And what's going to happen to the rate of dissolving as time goes on? It's going to go down until eventually what happens? They equal, and we get to an equilibrium. And when we hit the equilibrium, at this point, the solution is saturated. Up until that point, the solution is unsaturated. Yes. Solute? Yeah. Yeah, so if you have not put enough in to saturate it, you will simply end up with an unsaturated solution that is not at an equilibrium, and it's not moving towards equilibrium because there's not enough reactant. Like, so if you did not put enough of the solid in, you don't have enough reactant to get to equilibrium. It just goes to completion, and then you're like, oh, well, yeah. But while you're getting to equilibrium, there will be recrystallization happening. So anytime you have ions, there's always going to be a little bit of recrystallization. But if you have an unsaturated solution, you might get like 2 little ions coming together, but that's not enough to really do much of anything, and they'll break apart soon enough. So you're not going to end up with any solid forming in any great extent. So you wouldn't even see, whatever solid forms would be too small to even notice. Yeah? Okay, so if you put some solid into the solute into the solvent, we have a high rate of dissolving. So here we place AB, solid in water, and it just dissolves, starts dissolving. As time goes on, we start getting some of these ions, and so we're going to start getting some recrystallization. And basically the concentration of ions will continue to increase until either we run out of solid solute, okay, so all we have left is A and B, or the rate of dissolving equals the rate of recrystallization, and this means we are at equilibrium, and this means we have a saturated solution. So if we run out of solid, we continue to have an unsaturated solution. But if we get to the point where dissolving equals recrystallization, oh good, look, it says what I said. Oh no, what happened? What is happening here? Oh, page 29 comes after 30. That's exciting. Good Lord. Oh, it goes backwards. Does yours go backwards? No, what is happening? Oh my gosh. Okay. We might have a little problem here. Let's just see. 3.2b. I'm going to just reprint it out really quickly. Ay. That's crazy. Okay. Chem 12. Solubility. 3.2b. There we go. Okay, file, print. Okay. OneNote, desktop, print. I don't know how these things happen sometimes. It's a mystery. It's a mystery. At any rate, here we are. We were here and we have a saturated solution, and that saturation solution, as we said, it contains the maximum amount of dissolved solute. And if we have undissolved solute present, it will be at equilibrium. Okay, and you can actually see, I don't think we paid much attention to this diagram here. This is unsaturated. This was on our previous page. And you can see dissolving. There's lots of dissolving. But there is much less recrystallization. And same thing here, except for once we get to the saturated solution, every time you get some dissolving, you get a corresponding exactly the same amount of recrystallization. So how do, yes, sorry.
The saturated solution definition says that undissolved solid.
Yes.
On the back page says undissolved solid, but not yet.
So if you have an unsaturated solution, yes? So in an unsaturated solution, if you have undissolved solute present, you are not at equilibrium, but you are moving towards equilibrium. So you can have an unsaturated solution with solid present, and you can have a saturated solution with solute present. See how we have our solute here? Solute. But this is not full yet. So it is unsaturated. And the rate of dissolving is greater than the rate of recrystallization. Yeah? So that's for an unsaturated solution. I'm just going to do the saturated and then we'll come back to you, okay? Now, in our saturated solution, you can see now this is full now. Yeah? And we still have solute. But here, dissolving rate is equal to recrystallization rate because we have, the solution is now full. Before, it was unsaturated. The two rates were not equal. Now they are equal. So this is a saturated solution. Victoria. Sort of. It depends on how you define it. I know some people get really wound up and they're like, you cannot have a saturated solution unless you've got solid there for there to be an equilibrium. I've never seen that like tested anywhere, like in terms of having to define it that way. So what you could do is you could create a saturated solution and then you could filter out whatever solid is there. And that would leave you with a just barely saturated solution, right? So it's like saturated, but there's no extra stuff there. Yeah. You could do that too. You could calculate the molar solubility and then put exactly that amount in, but anytime you're measuring things, you're going to be a little bit, it's going to depend on the temperature. It's going to depend on your exact volume. How precise were you in your measurements? So probably the best way to get the actual saturated solution is to just add solute in and keep stirring it until you're like, oh, I got some solute left over, and then filter that out and you'll be left with as saturated as a solution as you can get. That when you've filtered out the solid, you no longer have an equilibrium because there's no solid there. Yeah.
Greater than or over S, which is higher than Celsius.
Yeah.
Once the solution will drop
so it's interesting when you heat something, if you cool it down slowly enough, you can actually get it to be what they call supersaturated. You've managed to get more ions dissolving than would normally be at room temperature. And if you cool it down slowly enough, they just sort of hang out where they are and they're like, I don't need to recrystallize yet. I'm happy here dissolved in the water. And then what you can do is to a solution that has been supersaturated, you can often, you'll scrape the inside of a beaker with, say, a glass stirring rod. And that little scrape just causes enough disturbance to the system that all those little ions are like, oh, there's little ions next to me. Click, 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 just like a bunch of magnets that, I don't know if you've ever seen anybody play that game where you have magnets and you add them and you add them and you add them and you add them and they don't come to, have you ever seen that game? It's basically you just have a string and then you put a magnet in there and then another person puts a magnet in there and you keep trying to put in magnets until it all goes click, 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 click. And so what supersaturating does, it allows you to put more magnets in there and all of a sudden it's as though you just pushed one of them and the whole system goes and anything that can crystallize out will crystallize out at that point. It could be. I don't really know much about super freezing water, but it sounds similar. Yeah. That's probably exactly the same sort of thing. Yeah. All right. So this brings us very nicely to method 1 of making a saturated solution, which is the dump and stir method. That is the official name. No, it's not. That's just what I call it. You dump in the solute and you stir it. And then you just keep doing that until some solid remains, which means you now have a saturated solution. So dump the solute, stir it, repeat until some solid remains. That means you have a saturated solution. You have the maximum amount of dissolved solute. When you do this, it means that the ions are going to be present in that X to X or X to 2X concentration. Okay, so the ions are present in proportion to the coefficients. So if we have CaF2, let's say, for example, concentration of CaF2 was 0.01 molar, then the concentration of calcium would be, what would the concentration of calcium be? 0.01 molar. And the concentration of fluoride would be 2 times that. And that is true anytime you dump and stir, because that is where are the ions coming from? They're coming from that solid. But there's another way to make saturated solutions. Yes, sorry.
How can it be the concentration of iron can be more if not all of it is
Because when we say the concentration of CaF2, that means how much CaF2 dissolved. So it's kind of like when we say if I was to say the concentration of HCl is 1.5 molar. Yes? Well, in reality, how much HCl is there once I put it into water? There's none. But I still say, how much did I dissolve in the water? I dissolved 1.5 moles in 1 liter. Yeah? So for calcium fluoride, not all of it dissolved, but how much of it did dissolve? 0.01 moles dissolved in 1 liter. And then the rest of it did not. So let's say I put in 2 moles, you'd still be left with 1.99 moles undissolved. Is it the what?
basically the initial concentration.
The initial concentration, yeah. Yeah.
But it is not the same thing as like CaF dissolved.
No, it would not. Like you would put in more than enough. Okay, so to make a solution, you would put in more than 0.1 moles in 1 liter.
Is the concentration of CaF2 what we doing later on?
Yeah, you might need to calculate this later on. So for example, let's say we did this and we filtered out all the extra. You might then be able to titrate this to figure out the fluoride concentration. And if you knew the fluoride concentration, you could find the calcium fluoride concentration, and that would give you the solubility. Yeah? Or you could filter out the extra solid, and then you could evaporate the water, and the mass that is left behind, you would then have the mass that was dissolved. Does that make sense? So if you filter this out, if this is gone, you're left with only this. And if you've taken the mass of the beaker ahead of time, yes, you could then just wait for the water to evaporate, or you could heat it a little bit. You don't want to heat it too vigorously, otherwise, there's ions escaping with spatter and stuff like that. But if you just wait for the water to evaporate and then you wait again, you would know the mass that was dissolved in that water. And you could say, I have that many grams in whatever that volume of water was. And then you could figure out the concentration from there. And that would be the solubility. Yeah? Oh, look. We always write equilibrium equations with the solid on the left. Did I tell you I was going to tell you this a million times? Look, I'm telling you, it's been, we're only at 999,000, not a million yet. Okay, so there we are. Remember, this is different than what we use for a precipitation reaction. A precipitation reaction, where does the solid go? Solid goes on the right. And what kind of arrow do we use? Which of these two would we use for a titration? Would we use the SEE, or would we use the PE? For titration. Now, This would be if we were titrating fluoride with calcium, which is a different situation entirely. We would not be using this calcium fluoride that we had just made. Okay, we might have sodium fluoride and then precipitate it with the calcium. Okay. All right. Whew. Saturated solution definition 2. A solution in which the dissolved substance is in equilibrium with some undissolved substance. And this is the definition I was talking about, where I don't think it really... Do you need to have that undissolved substance to have a saturated solution? Technically, yes. Can you kind of say, oh, well, I have a saturated solution if I dump and stir and then remove the solid? Yes. Okay, so just don't get too worked up about it. Okay? Don't worry about it too much. So this leads us to method 2 of making a saturated solution. And this method 2 is mix and match. Okay? So you're taking some ions from over here, and you're taking some ions from over here, and you are mixing them, and they match together, and they form a precipitate, because the solution is saturated with whatever is precipitating. Yes? So if you mix two solutions and they form a precipitate, you have successfully saturated that solution. Because if it wasn't saturated, a precipitate would not form. Okay, so what would this actually look like? This might look like we have sodium chloride. Yes? And in this particular example, let's say our sodium chloride is 0.008 molar. Okay? So we have 8 sodiums and we have 8 chlorides. These numbers are ridiculous. Okay, just work with me. Now, let's assume that our silver nitrate is 0.005 molar. Yes? With me so far? Okay. Now, when I mix these two, I put these two together, and I mix them together. Silver and chloride, what do silver and chloride do? Silver and chloride will precipitate. So, what happened? Who was the limiting reactant here? Who is the limiting reactant?
Silver.
Silver. Silver is our limiting reactant. Okay, because we got Ag plus Cl gives AgCl solid. And it's 1-to-1, but we have more chlorides than we do silvers. So 5 of those are going to precipitate, right? We got 1, 2, 3, 4, except for, remember, it is slightly soluble, right? It's low solubility. So we still have a little bit dissolved because this is AgCl is low solubility, so a tiny amount remains dissolved. I can't draw enough to make this actually look like a tiny amount. I would have to draw millions and millions of particles, right? And have like one sitting there. Oh, I'm dissolved, right? So I've only drawn 8. So the proportions here are ridiculous. Okay, but there's our thing. All the chloride is still floating around. or no, not all the chloride. Some of the chloride is still floating around, but you'll notice I have more chlorides than I do silvers. Yes? Yes. Yes. So I would, in this case, I would be thoroughly separating out the silver. Now, what about these guys? Too small to matter if you're trying to separate out the ions. Okay? Too small to matter, which is why when we write the precipitation reaction, we write it as going one way. Yeah? It's only when we're looking at KSPs where we're like, oh, but it really does matter. We're going to, KSP, oh, yeah. Right? But when we're like precipitate, we're like, I don't care about that much. Right? Yeah? Okay. Now, I might have a different situation in which I have only 6 sodiums and 6 chlorides, and I have 6 silvers and 6 nitrates. And guess what? I have AgCl, which has precipitated, yes, and I still have some silver and some chloride floating about. So let us write the net ionic precipitation equation. We have Ag plus Cl minus goes to AgCl solid, aqueous, aqueous. Now we're going to calculate the KSP in situation A and situation B. Because remember, back up here, we had 1 silver chloride, but we also had 3 extra chlorides, right? Over here, we had a silver and a chloride, and we had a silver and a chloride still undissolved, right? Okay. But if we do our calculation here, we have, in situation A, we have 1 Ag plus, and we have 4 Cl minus. Over here on the right, we have 2 Ag plus, and we have 2 Cl minus. Can we agree, though, that in both of these situations, we have a saturated solution of silver chloride? Right? If I were to try and cram any more silvers or any more chlorides, they would not dissolve. Yes? Well, let's look at our KSP. KSP is equal to the concentration of silver times the concentration of chloride, which in this case is 1 times 4, which is 4. Over here, KSP is equal to the concentration of silver times the concentration of chloride. And in this case, that's going to be 2 times 2, which is 4. The KSP will be the same no matter how we arrive at our saturated solution. So if I put in the same amount of ions of all types, I'm going to end up with the same concentrations. Yes? But if I'm mixing 2 solutions, what are the chances that I'm perfectly going to put in the same amount of silvers as chlorides? What are the chances? Very low. So my chances of getting a result like this are much more likely than actually having them be perfectly matched. Yes? And I chose these numbers because they're easy to work with. But this is saturated, and the concentration of silver does not equal the concentration of chloride. And that's because this was not dump and stir. I did not dump silver chloride into the water, stir it, and have a 1-to-1 ratio. I dumped in some silver from source A and some chloride from source B. So I mixed and I matched, and so the concentrations of the ions are different. Okay. In equilibrium, KEQ is, or KSP is always constant unless you change the temperature. Remember, in an equilibrium, do concentrations have to be equal? They do not have to be equal. So if you form a solubility equilibrium by mixing two different solutions, the ion concentrations will not be in proportion to the coefficients. This is mix and match. On the other hand, if you do dump and stir, you will get in proportion to the coefficients. And in section 3.3, we're going to do a whole bunch of math where in some instances, the two ions are proportional. They're always 1-to-1 or 2-to-1. And in other instances, they can be, 10 to 1.78 or, 3.33 times 10 to the negative 4 to 8.72 times 10 to the negative 5. Who knows? Okay. And we're going to leave it there for today because that's all she wrote. And tomorrow you have your test. So your homework is to study for your test. Okay? If you are a person who needs extra time on tests, you may, if you wish, come 15 minutes early. Okay? And start 15 minutes early. Because my other blocks, sometimes they want to take 10 minutes at the end or 15 minutes at the end. And I'm kind of okay with that. But at the same time, I don't want it to be unfair where they get extra time and you don't. Do you know what I mean? So I will not allow them to go past 15 minutes into lunch. And you guys would have to, you can, if you wish, start 15 minutes early at lunchtime. Yes? You have a question about? Yes. Why can no more dissolve further? Just the forces between the ions become too close together, and the forces between the ions at that distance becomes too strong, so they will literally like click together. They end up next to each other and they're like, oh, hello. Yeah. And then when there's enough space again, then they're like, oh, I will stop. But then every once in a while they get close enough and so they precipitate, but then another one will come out. And yeah, I'm sure it does. I haven't really gone into that much. Senya, you had a question as well. 24 multiple choice, 16 written response marks. Not questions, marks. Pardon me? Yes. Is there anyone else who did not get their quiz back? Yeah, I got them. Victoria and Katie. I'm sorry for not this. Again.
Let me see.
Oh, it's lunch time. Yeah. Oh, yeah. Okay.
They off. So you guys stuck with what they want to be. Walk that one. So you walk on that would be. I mean, I don't see. All this time of application. And like if I love that. So like, what the I do? I want it. It's all my I get it. We don't talk about that. We don't talk about that. The glaze isn't perfect, so I glaze it over again and it's getting hot. Why did you make that? So I just take the bottle and it over first. He's right. Oh,
They fly into study space if you wish to study. Fly it out. And you need to find another place for me. Oh,
Also,
I need to find another place for me.
it actually pretty. It's actually pretty. Well, now
I
really fall in love with it.
We're done.
Yeah.
So now I'm just, I got this. Yeah, it's fine. Oh, you're
Every day. No, someone thought like one thought like okay, it's actually like you know how the difference between a this one person thought like swings all the way in so I don't like yeah wow I swear we were born on the same day.
Of course.
I may have accidentally break wrong.
Why do you think the sun is I don't know. I don't know. Because I'm just that far. I always like get all
Hi. I was just saying every day I have something I was wearing and stuff I was sorry. John. Like everyone if it's important to value. I'm yeah. I would go because it doesn't really go beyond all the
Oh my God.
Of course.
Yes, I forgot about that, yes. Like 3 days.
So you have 1.5 left. Okay.
Oh, I can link transfers. I can use it for other quizzes.
Oh, hell yeah. Probably, yes. Victoria, there you go. Let's find it.
Also, my stuff is not because I unlocked it.
So that's basically saying. So that's like perspective. I just move on to the side. Yeah. Look at. You still have no time.
There we go. And we want to go to Chem 12, and we want to go to review.
No, actually, I'm not person. I like my mug.
That's so cute. Did you make it?
Yeah, we made it in art class.
That's so cute. Oh my god. Okay. Acid base 1. What can I do for you, Tiago? Well, give me a good reason why.
Because I have a math test tomorrow.
Okay.
It's on trig identities, and I seem
Okay.
to be very bad at trig identities.
Yeah.
Thank you.
Okay. Yeah. Just make sure, like, come in at lunch because then otherwise you won't have enough. Oh, but there's also flex at the end of your block, so you might be okay. Yeah. Okay. Cool. Okay.
It's not clear, but like, so what's the sig fig for this? Do I just use the sig?
2 sig figs.
Oh,
Yeah.
in the pH, right?
Yeah.
And then, oh, for 6, is H2PO4 minus a diprotic acid?
Yes.
It is, right? Because it has 2.
Yes.
Anything with 2 H's has diprotic. This refers to the equilibrium and concentration, right? Contains twice as much conjugate base.
Yes. Okay. Finishing. No. Layout. Oh. Basic. How do I make it a 2-on-1? Come on.
Okay, thank you.
Two pages per sheet. Yay.